Hello and welcome to my video. Today we will solve the problem that is actually very easy but contains basically every bit of important stuffs of calculus, including derivative, integral, limit, and continuity. Right, so the problem says that we have to define a function fx on x greater than 0 so that the fx satisfies these two conditions. So first, fx should be continuous for all positive real number x. And second, if we define gx as x minus 1 times fx, then g prime x, the derivative of gx, is 1 over x. Of course, for positive x. Alright, so how can we find this function fx? Now, before we do anything, let me remind you that fx should be defined on every value of x that is positive, which means that fx should be also defined at x equals 1. We shouldn't miss that. So with that in mind, let's find fx. And we are going to start from here. Since g prime x is given as 1 over x, we can obtain gx by simply integrating that function. So we have ln x plus constant c. We don't need the absolute value for ln x because we have this condition that x is positive. Now, this constant c can be determined using the fact that gx is defined as x minus 1 times fx. So it means that x minus 1 times fx equals ln x plus c. And if we plug in x equals 1 here, we have 0 equals 0 plus c. So therefore c must be 0. So we have x minus 1 fx equals simply ln x. Of course, when x is greater than 0. Now, the next natural step would be, of course, dividing both sides with x minus 1. However, if we want to divide both sides with x minus 1, we must add a new condition that x minus 1 is non-zero. Therefore, we have fx equals ln x over x minus 1 when x is positive and x is not 1. This condition is now added, so we have this expression for fx, but we are not done yet. Since it is stated that fx is defined on all positive x, it should also be defined at x equals 1, which means that the value of the function at x equals 1 must be determined. And for that, we are going to use this continuity condition. Since fx is continuous at x equals 1, f1 can be defined as the limit of fx when x approaches 1. Now fx is defined like this when x is not equal to 1, so we have limit x approaching 1 ln x over x minus 1 here. We can use this expression for fx because x approaching 1 means that x is not exactly 1. So now we have to evaluate this limit. And actually the value of this limit can be found by using famous L'Hopital's rule. So if we take derivative at numerator, we have 1 over x. And if we take derivative at the denominator, we have 1. So the value of the limit is 1. Or you can also find the value of this limit by letting x minus 1 equals t. Then we have t approaching 0. And we have ln 1 plus t over t, which is limit of ln 1 plus t to the power of 1 over t. And this part approaches constant e by the limit definition of e. So we have ln e and therefore 1. So either way, we can find that the value of f1 equals 1. So now we have our final answer that fx is given as ln x over x minus 1 for positive x that is not equal to 1, and fx has the value 1 at x equals 1. So this is our answer. So we are basically done here, but if you are curious, you can check this answer by doing things in a reverse order. That is, using this fx, gx is defined as x minus 1 times fx. We must also define gx separately. So when x is not equal to 1, we have x minus 1 times this. So we have ln x. And when x equals to 1, then f1 equals 1. So we have 1 minus 1 times simply 1, which is 0. But since this 0 is nothing more than ln 1, this means that basically gx equals ln x for all positive real numbers x. Therefore, the derivative of gx is simply 1 over x for all positive values of x. And that's all for this video. Thank you for watching, and I will see you in another video.